homework questions? Anything on the? No, yes, no questions?
Can we do number 57?
Sure. Just pull it up here. Oh, just the sine squared one?
Yeah.
Okay. So number 57. The integral of sine squared x dx. And we're going from, oh, I gotta try and read this. I can't even. Negative pi to pi, okay. And from negative pi to positive pi. All right, so in order to do this one, oh, and I see that, Rebecca, 61, yep. So this requires the power reducing rule because there's just a sine squared there. So we have to go down to this. So we get 1 and sinus minus cosine of 2x, all of that over 2 dx, and still minus pi to pi. So that's the integral that we have to do. There's no other fooling around with this thing that'll get us anywhere. The 2 is just a constant, so I'm going to pull that out front, just get it out of the way. And that leaves us with 1 minus cosine of 2x dx. All right. Okay. So far, so good. Now we integrate. The integral of 1 with respect to x is x. And this is a little u sub. This becomes 1/2 cosine of u. So that'll come up a lot in these things. Oh, wait a minute. Got some folks coming in here. Oh, and I'm also recording this. So class is going to be on the little short side, so I'll be able to record this and put it up later. All right. So the minus stays there. So the integral of cosine is sine. So we get minus 1/2 sine of 2x. And then we go from negative pi up to pi. So, okay, so far, Brandon? I think that was
yeah, I'm good up here if you want to continue. It's up to you.
Just out of curiosity, what part did you stumble over?
What confused me was just the trig identity, just using that in the beginning.
Oh, the power reducing. Yeah.
Yeah.
So if all you have is a cosine squared or a cosine to the 4th or something, or just a sine squared to the 4th, it's going to be power reducing formula.
Got it. Thanks.
Yeah, when you have a mix of sines and cosines, it'll often result in a u substitution somewhere. Nicholas. I did that right here. That's the 1/2 part right here. So if we were to do this derivative, so we were to do the derivative of sine of 2x. So it's a good question you asked. I'm glad you asked us. So let's say that y is, oh, and so the rest of this problem is you just put the pi and the negative pi in there. So you can do that arithmetic on your own. So if we do this integral, we get y prime. That 1/2 is a constant. And now this is the chain rule. A u substitution is the reverse or the inverse of the chain rule. So chain rule is derivative of the outside. That would be cosine of 2x. And then you do the derivative of the inside, and the derivative of 2x is 2. And they cancel out, and that takes us back to the cosine of 2x. I'm glad you asked that question. Right. And then Rebecca, number 61. Right. So this is from 0 to pi over 3, and it's cosine t on top of 1 plus sine t and dt. There we go. Okay. So yeah, there's nothing squared up there. So nothing cancels out. Nothing squared, so no identities kind of go. This one can be done by a U substitution. So I'm going to let U equal 1 plus sine of t. And we'll do the derivative. So the derivative of U is du. The derivative of 1 is 0. And the derivative of sine is cosine t dt. This one's kind of a stinker of a problem because once you see it, it's like, how was I supposed to know how to do that, right? So now we become this. So here is, this is du right here. So this problem becomes 1 over u du. And the integral of 1 over u is the ln of u. And then I didn't put the limits on here because I'm just doing this one a little bit differently. Now I'm going to replace the u by this. And so we get the ln of 1 plus sine of t from 0 to pi over 3. And I'll stick those numbers in there in just a minute. So far so good, Rebecca? Oh, thank you. Yeah, that's all right. It's really tiny type in that book, and it's really dark in here, and my eyes are really old. So far you're good with this? Yeah. Yeah, these can be very frustrating. You stare at it for 20 minutes and not see that, oh, all I have to do is this. So we'll do the ln of pi over 2, plus the sine of pi over 2, which is 1, minus the ln of, well, 0, and then the sine of 0 is 0, so all of this is just 0. So there's your final answer right there. Yeah, got to have those identities in your back pocket. You kind of have to, so every problem is different. That's why I've said there aren't really any rules that can be always do this. I can just give you some sort of guidelines to help you get started. And it's a lot of the reason why nobody likes Calc 2. Calc 1, you had, what, 17 rules for derivatives, and they always worked. You just identify the function and go and do it. All right, both good questions. So,
wouldn't you subtract by the ln of 1 because it's 1 plus sine of 0?
oh, yeah, and the ln of 1 is 0.
Oh, okay, gotcha.
Yeah.
Thank
Oh, that pi over 2 shouldn't be here. Crap, this should be 1 plus 1. Oh, I'm sorry, the whole answer is 2. I accidentally put a pi over 2 here, shouldn't. Sine of pi over 2 is 1, so 1 plus 1. So the final answer is the ln of 2. But I think that was you, Jordan. Yeah. If you think I made a mistake, I probably did, so call me out on it. But in this case, I was okay. All right. So last time the homework was integrals with sines and cosines. Tonight, the topic is tangents and secants. And they can be a little more frustrating because we're kind of familiar with sines and cosines. Derivatives of sine, cosines, integrals of sine and cosine, you see those a lot. But secants don't really come up a whole lot. So this can be a little more frustrating. So here's where we'll start here. We have cosine squared of theta plus sine squared of theta, oops, always equals 1. That's the one to start them all with. And now I'm going to divide everything by cosine squared of theta. Now, that's actually a little bit of a cheat. Technically speaking, you're not allowed to divide by trig functions. You're not allowed to divide by a sine or a cosine. Anybody know why? Sines and cosines and tangents and secants can take on the value of 0. So if you divide in an algebra equation, you divide by cosine, you could accidentally be dividing by 0 and not know it, and things get strange. But so we're going to do that here just to get here. So cosine squared divided by cosine squared is 1. Sine squared divided by cosine squared is tangent squared. And 1 over cosine is secant, so 1 over cosine squared is secant squared. And there's an identity that's going to come up a bunch. So anytime you see a secant squared, you can replace it with this. Or if you have a problem, you can replace tangent squared by that. So these two identities will come up a bunch. Okay. The other thing is we need to be able to do integrals and derivatives. So tangent, we have tangent x and we have secant x. I'm going to go down here, I'm going to do derivative. The derivative of tangent is secant squared. Anybody remember what the derivative of secant is? It's not one you run into a bunch. You might not remember it. They're all in your book somewhere. Anybody happen to remember?
Is it like secant x tan x?
Yep. Derivative of secant x is secant x times tangent x. So starting here, those are the derivatives. Starting at the bottom and coming back up, the integral of secant tangent is secant, and the integral of secant squared is tangent. So these two identities will come up a bunch, and the derivatives come up a bunch as well. All right. So here we go. The integral of secant to the 4th power. Now there's never rules I can say, when you look at this kind of problem, always do this, because every problem is a little bit different. But one way, if you're staring at it, stare at them a lot because you're not really sure what to do. Trig identities all depend on something being squared. So I'm going to break this up into secant squared dx. You just have to do enough problems, you sort of get a feel for it after a while. Well, I know that secant squared is the derivative of tangent, and I can rewrite this secant squared into a tangent using that identity. So secant squared, it's 1 plus tangent squared x, secant squared x dx. Just pause there in case somebody's got a question. Looks like we made it worse, right? Looks pretty simple here. Now it kind of looks like it blew up and made a mess all over the floor here. All right, anybody got a suggestion for what comes next?
What's the goal of switching that to 1 plus 10x?
Because now this turns into a u substitution. Can't integrate this. Can't integrate that. But what I'm going to do, this is going to be my du, and tangent is going to be my u. So this is now a u substitution. U is equal to tangent, not tangent squared, u is just the tangent, and then du is secant squared x dx. All right, so now this problem becomes the integral of 1 plus u squared du. And now it looks not so bad, finally. Now we just do the regular integral here. The integral of 1 with respect to u is u. The integral of u squared with respect to u is 1/3 u cubed plus a constant. And the last step is to replace the u's with tangent. So the final answer here is tangent x plus 1/3 tangent x cubed plus c. And again, I highly recommend that you do the derivatives of the answers.
Isn't it 1 plus tangent squared x for the u?
No, it's just tangent.
Okay, gotcha.
If I were to do, and I see that a lot. So the last time I made 1 plus sine the u because it was sine to the first power, and the 1 was a constant. If we said that u was equal to 1 plus tangent squared, right? If we were to say that, now we'd have to do the derivative. So du, the derivative of 1 is 0, but the derivative of tangent squared, that's the chain rule. The derivative of tangent squared is 2 times the tangent of x times secant squared of x. And that would just cause a bunch of problems. Now you got another secant squared to deal with.
Gotcha, that makes sense. Thank you.
So if you got something squared, don't make that the u, only when it's something to the first. But that was a good observation. I'm glad you asked that. Okay. Next problem. Pull one out of the book here. Let's see here. I'm going to do this problem two ways. This one has two solutions, or two methods that work, and they're both about the same. So I know the derivative of tangent is secant squared. Oh, okay. So this problem just turns into the integral of u du. Whoops. That's u, and there's my du right there. So the answer here, 1/2 u squared plus c is 1/2 tangent squared x plus c. Okay, so that was pretty straightforward. But there's another version. Or I can do this. I can rewrite this as the integral of secant x, tangent x dx. So secant squared I wrote as secant times secant. Now, secant times tangent is the derivative of secant. So now this can be our u, and all of this can be our du. And we still get this integral, the integral of u du. So they look the same at this point. And we get 1/2 u squared plus c. They look the same at this point, but now my u in this case was secant, so I get 1/2 secant squared x plus c. Both of those answers are correct. They look different, but they're not different. They're just a different way of saying the same thing. So a lot of times you have some options here. Okay. Take another another one.
Wouldn't that mean that secant squared x means equals tan squared x?
They don't equal each other, but those two particular answers will, on certain intervals, give you the same curve. They'll have the same graph. And it's because things are being squared. So that's why sometimes when you're doing some problems and you maybe look in the back of the book, the answers you see in the back of the book looks nothing like the answer you have, but you can still be right. You just have a different form. Tangent squared over secant squared, all of that dx. Okay. The first thing to do is stare at it for a while. So there's a couple of things to do here. So this one looks, now you got a secant squared down in the denominator. So here's, again, there's no rules, but I've always found when I'm doing stuff like this, because tangents and secants, we just don't have that familiarity with them that we do with sines and cosines. So sometimes one thing you can do is rewrite everything in terms of sines and cosines. So secant squared in the denominator, I can bring that secant squared up and it becomes cosine squared. Because secant and cosine are upside downs of each other. They're reciprocals. And now I can do this. How did I get there? This turns into this. Do you see how? I'll show you in a minute in case you don't.
Tan x is sine over cosine, so the cosines cancel out.
Yeah, so tangent squared is sine squared over cosine squared, and then they cancel out. And then this is the very first problem I did. Brandon asked me this one from the homework problem from the last time. So use the power reducing formula here, 1 minus cosine of 2x over 2. And that's what I did right in the beginning of class. All right. So sometimes getting rid of tangents and sequence and using sines and cosines, nice things can happen. And sometimes not, but it's just another thing that you can try. Now we'll do a definite integral. So trig functions come up a lot. It's important to be sort of familiar with them. Hang on just a minute. Whoop. Okay. Whoop. Whoop, whoop, whoop. All right. Integral from 0 to pi over 3 tangent squared x dx. So there's our problem. So what are we going to do with this? Any ideas? I'm just going to go right to an identity. That comes from cosine squared plus sine squared is 1, like we did at the beginning. So tangent squared is secant squared minus 1. Now what do we do?
You just integrate?
Yeah, we just integrate. Secant squared is the derivative of tangent, so the integral of secant squared is tangent x, and the integral of -1 with respect to x is minus x, and then we go from 0 to pi over 3. So these can be kind of frustrating. Turns out, oh, wasn't a lot going on there. And then you look at the next problem and you stare at it for a while and you're just not sure even how to begin. So that's completely normal and it'll be frustrating. So some advice I can give you is if you're not sure what to do, just start rewriting things and maybe something will sort of pop up. Okay, so now we have to put these numbers in. So this gives us the tangent of pi over 3 minus pi over 3 minus the tangent of 0 minus 0. And now we're going to take a little trip down memory lane and go to everybody's favorite, the unit circle. In case you don't happen to know what the tangent of pi over 3 is. It's not a bad circle, is it? So in order to do the unit circle, everything is done in terms up here of the first quadrant. And then those numbers translate into the other quadrants just by changing the positive and negative signs in them. So there are 5 angles you should just kind of know. So we have 0, and that's 0 degrees or 0 radians. The next angle up is pi over 3. The next angle is pi over 4. The next angle is pi over 6. And this last angle up here is pi over 2. So 90, 60, 45, 30, 0. And the sine and cosines of all of these go with the particular point. This point has the this point has coordinates 1, 0. This has coordinates square root of 3 over 2, 1/2. This one up here is 1/2 square root of 2 over 3.
Sorry. Isn't the first one pi over 6? Then you have pi over 4, then pi over 3.
Thank you. I would have caught that. I do get, yeah, I listen now.
I'm very confused for a second there.
Yeah, my fault.
I had to actually check the book.
Yeah, these are all in the back cover of your book. There's a whole page, all the identities and everything. So here's how I remember how these numbers go. Right here, this is x equals 1. So right here is x equals 1/2. And over here, this is y equals 1/2. So for pi over 6, you see you're up to this point right here. So the y value is 1/2. For pi over 3, you're directly over x equals 1/2, and that goes there. So it's just a way to remember it. And then as these translate around the circle, these values stay the same and just the positive and negative signs change over here. So for the problem we just had over there, we need the tangent of pi over 3. That was in the problem. So we go to pi over 3, and tangent is y over x. So for all these angles, this is cosine, sine, cosine, sine, cosine, sine, cosine, sine. And up here is, oh, I didn't do that one. So the x is the cosine, the y is a sine. So we get square root of 3 over 2 over 1/2, which is just square root of 3 because the 2's cancel out. We also had at the other end, we need the tangent of 0. Well, the tangent of 0 is 0 over 1, which is just 0. So those are the values for that last problem. And so this problem becomes, this is the square root of 3 minus pi over 3. This is 0 and that's 0. So that's the answer to that problem. And that's exact. Anything else is calculator. And that's it for tonight. There's about 6 or 7 homework problems with tangents and secants. Some of them like this. You just go through those. So let me see if there's no other homework questions or anything. That's all I wanted to do tonight. This is still in the same section. I'll upload the homework and this recording, which I don't really need anymore. Hang on a minute.
I'm a bit confused where to find homework and recordings.
They're all in the same place.
Where is that?
Up in Canvas and files. Yeah, the recordings are MP4 files. Everything's in the same spot. Everything goes into files all semester long.
Oh, I see it here now. Okay.
Yeah. So I'll be able to keep the last one up because these are sort of small. So last time we were in section 8. I think it's 8.3, whatever. Yeah, 8.3. So we did sines, cosines tonight with tangents and secants. That's all we need to do tonight. I'm not going to start the new stuff because you need to be good at this stuff first. The next section we're going to do is something called trigonometric substitution. It's like a U substitution, but not with U's. We're going to put in thetas and have some trig things in there. So you've got a few days to practice all this, and also keep going back and practicing some integration by parts. Do some of the even ones. You can ask homework questions on those. Just do some of the even ones. Just keep up practicing with them. And that will be good. So anybody have any questions? Hi, Naxon. I don't know if you were here before and dropped out or if you're just getting in here for the first time. But we're kind of done. I did record tonight, so I'm going to upload that. We just did some integrals with tangents and secants in them. I did about 4 examples. It's a very short class tonight. So anybody got any questions? Anybody's feelings hurt that we're not going to go for another hour? I mean, I could still do more examples, but they're just the same over and over again. Well, all right then. I will upload this file to where it is, and I'll put the homework up there. And if I haven't already, I don't know if I already put it up or not. And have a very nice weekend, and I'll see you all on Tuesday. Email me if